This video is prepared by Avya Classes. Please subscribe the channel, raise your doubt and watch the video for sure success in JEE, AIMS and NEET. First problem I have picked from AIPMT 2009. An engine pumped water continuously through a hose. Water leaves the hose with a velocity v and m is the mass per unit length of the water jet. What is the rate which kinetic energy is imparted to water? So I just first draw the figure. Let's suppose this is the hose pipe which throws water with a and mass m be the mass per unit length of water, and it throws the water with a velocity v. So it means velocity v is equal to length divided by time, as we know that velocity is equal to length divided by time. So for t is equal to 1, length is equal to v. It means in 1 second the water moves through a distance equal to v. So suppose at the start of 1 second water was there, and we just consider the water which was close to the starting point of hose. The same water has reached a distance equal to v meter in time t is equal to 1 second. So I just write here t is equal to 0, write here t is equal to 1, and the water has traveled a distance equal to v meter. So it means if I have to calculate the rate of mass per second or rate of water per second, then it is equal to v into m, as m is the mass per unit length and v is the length in which we have to consider the water for 1 second. So rate of water per unit second is equal to v. Now we have to calculate the rate at which kinetic energy is imparted to water. So means we have to calculate k dk by dt, or how the kinetic energy is imparted. So basically we have to calculate rate of kinetic energy per second, and it is equal to 1 by 2 into the rate of mass per second into v square, and is equal to 1 by 2 into mv into v square. So the value comes equal to mvq. So answer will be mvq by 2. So answer will be mvq by 2, and it is 2. So our approach will be that based on the problem we just calculate that what is the rate of water per second, and as mass per unit length was given and the velocity is given, so in the time 1 second the mass equal to mv has been considered, and based on this we just calculate the rate at which kinetic energy is imparted to water. Now this is the second problem from AIPMT 2006 mains, and a body of mass 0.8 kg has the initial velocity vi is equal to 4I plus 3j meter per second, and final velocity is equal to minus 6j plus 2k meter per second. Find the change in kinetic energy. So it's clear that the kinetic energy is equal to half mv square minus half mu square, and is equal to change in kinetic energy. So for this you just first calculate the final velocity. So final velocity vf is equal to minus 6j plus 2k, and is in vector form. If you consider this magnitude, then the value is equal to square root 6 square plus 2 square minus 6 square plus 2 square, and the value is equal to 36 plus 4 and square root 40. Similarly, the initial velocity is equal to 4I plus 3j meter per second, and if I take the magnitude of it, then magnitude of initial velocity is equal to square root 16 plus 9, that is square root 25. The change in kinetic energy is equal to 1 by 2, mass is 0.8 and 40 minus 25. So 0.4 into 15 and the value comes equal to 6 joule. So answer is equal to 6 joule. So it's pretty simple problem that you just calculate your initial velocity, final velocity, and directly apply the formula that change in kinetic energy is equal to half mv square minus half mu square. This problem is also from AIPMT 2004 means, and it's a good problem that a body of mass m falls from a height h and collide with another body of same mass. After the collision, the two bodies combine and move through a distance d till they come to rest. Find the work done against the resistive force. So basically it's a problem based on the collision, but we will discuss here such that you will get a brief idea about collision also and how we calculate the work done against the resistive force. So a mass m falls through a height h. Suppose this mass m falls through the height h, and here another body of mass m was kept in air and these two bodies collides. After collision, these two bodies move simultaneously through a distance d, then comes to rest. So here these two body velocity becomes 0. Here this mass has velocity also equal to 0. Here it has some velocity that we say it's v dash, and here velocity is equal to 0. And you have to calculate the work done against the resistive force. So basically these are some resistive force which acts in upward direction and force this body to stop after some time. So you have to calculate work done against those resistive force. So how we will solve this problem? First thing, that when after the collision, this if the two body move simultaneously, then that type of collision is called as perfectly inelastic collision. About this type of collision we will learn later in the collision chapter, but for the time being you just learn that when the two body after the collision move simultaneously or stick to each other and then move, then it's called as perfectly inelastic collision. That is, velocity of both body will be same. Second is that the momentum will be conserved in collision. Momentum conserved in collision. So our approach will be that we just first calculate the velocity of body after the collision, and secondly we just apply the value that how the energy is changed by the work energy theorem to get the idea about the work done against the resistive force. So first we calculate this velocity v dash. So when this mass strikes with the another mass, suppose this is mass A and this is B, so when mass A strikes with the mass B, then Pi is equal to Pf, that is initial momentum is final momentum, and initial momentum is m into velocity of mass A, it is equal to square root 2gh. As we know that when a body drops through a height h, then its velocity will be equal to square root 2gh. So its velocity is equal to square root 2gh. So m is equal to m into square root 2gh is equal to m plus m into v dash, and it is equal to v dash is equal to square root 2gh by 2 and it is gh by 2. So we just get the value of velocity v dash. Now calculate the work done against the resistive force. We just first apply work energy theorem and then we get the answer for this. So as per the work energy theorem, the work done by all forces is equal to change in kinetic energy. So it is equal to work energy theorem. So W is equal to delta K. So here the work done is, if we consider this part of motion, then here the work done was due to resistive force and work done was due to gravitational force. So first, when the ball was moving downward, so the gravitational force acts in the downward direction and its value is equal to mg. So, and if it moves through a distance d, then work done by gravitational force is equal to wg is equal to mg into d. Force and displacement both are in the same direction, so angle theta will be 0 and the value is equal to mgd. If I consider the work done by resistive force, then the resistive force acts in the upward direction and this is the Fr, which is the resistive force, and displacement in downward direction. So work done by resistive force is equal to minus Fr into d. Now, as per the work energy theorem, Wg plus Wr is equal to change in kinetic energy, and it is final kinetic energy is 0 and initial kinetic energy is 1 by 2 into 2m and into multiplied by v dash square. So work done by gravity is equal to mgd. In fact, it's 2 mgd because mass is 2m. So 2m into gd minus frd. In fact, minus frd, we just write wr here because you have to calculate wr, and it is equal to 1 by 2 into 2m and v dash square is equal to gh by 2. So we get minus wr is equal to, so minus wr is equal to twice mgd plus mgh by 2. So it means work done against resistive force will be equal to, work done by resistive force is equal to minus wr is equal to, if I take mg common, then it is h by 2 plus 2d. So this is the minus wr, that is work done against the resistive force. Wr is the work done by resistive force and minus wr is the work done against the resistive force. So work done against the resistive force is equal to mg into h by 2 plus 2d. So this is the important concept, that in the perfectly inelastic collision you cannot apply the conservation of energy. Like if you calculate, if you want to solve it through the conservation of energy, then it will be wrong. Like I just show you that the conservation of energy theorem will not be applicable in case of perfectly inelastic collision. The next problem is that a particle moves on a rough horizontal ground with some initial velocity v0. If 3 by 4th of its kinetic energy is lost in friction in time t0, then you have to calculate the coefficient of friction between particle and the ground. So I just first draw the figure. Like this is the particle which is moving with some initial velocity v0, and the frictional force mu mg acts on this. After some time t0, it's after some time, here t is equal to 0, here time t is equal to t0. So after time t0, its velocity will become, suppose its velocity is equal to v, then v will be such that the kinetic energy is 3 by 4th of kinetic energy will be lost. So kinetic energy final is equal to 1 by 4 kinetic energy of initial, as 3 by 4th is lost, and half mv square is equal to half mv0 square into 1 by 4. So from there we get v is equal to v0 by 2. So here we get v is equal to v0 by 2. Now we have to calculate the coefficient of friction. So if I can, as this is our frictional force, so acceleration or retardation due to friction is equal to minus mu mg by m, and it's equal to minus mu g. So basically, in fact, this is the acceleration due to friction if we consider a negative sign. If we say it's a retardation due to friction, then its value is mu g. And as it is constant, if you see that it is constant, so we just apply equation of kinematics in this case. And equation of kinematics say that final velocity is equal to initial velocity plus at, acceleration into time t. So final velocity is equal to v0 by 2, and it's equal to v0 minus mu g into t0, because the whole process has finished in this time t0. So mu g t0 is equal to v0 by 2, and mu is equal to v0 by twice g t0. So if you see the option, then the option A will be correct. Mu is equal to v0 divided by twice g t0. This is the last problem of our kinetic energy section, and a ball is projected vertically upward with initial velocity. Which of the following graphs best represent the kinetic energy of ball as a function of time from the instant of projection till it reaches the point of projection? So if a ball is thrown vertically upward with some initial velocity u, then it reaches up to a certain height h, stops there, and then falls downward, reaches to the point of projection in time t0. So for the upward motion and the downward motion, the time taken is equal to t0, which is equal. Now you have to calculate, in fact you have to represent the graph of kinetic energy versus function of time. So the kinetic energy is given by half mv square, and v is given in this case of v is equal to velocity of ball at any time instant t, and it is given by v is equal to u minus gt. So as we know it from the equation of kinematic. If you get any doubt in it, you just go in my topic motion in a straight line to get an idea about it. So kinetic energy is equal to half mv square. So if I put the value of v square, then 1 by 2 m minus m into u minus gt square. So basically it's the motion of parabola. This graph is represented in terms of parabola, so the option will be straight away it's equal to C. So answer will be C. Anyway, we just discuss more about this graph. So kinetic energy is denoted by Ke, and if I make u minus gt, if I represent u minus gt by a capital T, then its form equal to 1 by 2 m into t square. So if you see this, then it's a form of y is equal to some constant. We just denote this constant by 4a into x square. So it's a form of, or in fact if I write it 1 by 4a, then its form of x square is equal to 4ay, and the standard equation of x square by 4ay, or the graph of x square by 4ay, is equal to this way. So this is the equation of x square is equal to 4ay. So now if you see this problem, this equation again, then kinetic energy is equal to 1 by 2 m u minus gt whole square. So just take g common from this, then we may write it into the form of t minus u by g ka whole square. So basically kinetic energy may be represented in this way also. So here t is equal to 0 for this right hand side will be 0 for the time t is equal to u by g. So for t is equal to u by g, we have kinetic energy will be 0, and this graph will be shifted by a distance equal to u by g. So the graph will be shifted by a distance equal to u by g. So the gap between these two is equal to u by g. So that's why this curve shifted by a distance u by g in the right hand side. So this is our time, this is our kinetic energy, and the actual curve will be this. So if any terms is subtracted from the time, then the graph will be shift in the right hand side. If we add some term, suppose the term will be in the term if the RHS will be of the form t plus u by g, then the graph will be like that. Instead of this, the graph will be shifted on the left hand side. So if any term is added, then the graph will shift in the left hand side. If any term is subtracted, then the graph will be shifted right hand side. So the answer will be C for this problem.